All right, let's talk about some of these conceptual questions. All right, so regarding, we'll start off with hypothesis tests. So the hypothesis tests will be, let's see. So regarding your null and alternative hypotheses, okay. So as far as decisions go, so the decisions are either reject the null and support the alternative, or do not reject the null and do not support the alternative. Or I should say not enough evidence to support the alternative. Okay, so we never say we accept the null. And then we'll never say we reject the alternative. Rejecting the null is essentially the same as supporting the alternative. And then failing to reject the null is essentially saying, or is the same thing as saying there's not enough evidence to support the alternative. Okay. All right, let's talk about what our p-values are. Okay, the p-value is the probability of observing the data you have, or something more extreme, if the null hypothesis were true. Okay, so for example, what does it mean to have a p-value of 0.07 for a hypothesis test for mu1 equal to mu2 okay, where y bar 1 is equal to 3 and y bar 2 is equal to 4.3. Oh, I guess I should say the null was mu1 equal to mu2, and then the alternative would be mu1 not equal to mu2. All right. So what does it mean to have a p-value of 0.07? This means that if the two population means were equal, then the probability that two random samples would have a difference of 1.3 or more, or negative 1.3 or less, difference of 1.3 or more or negative 1.3 or less, then the probability that two random is 0.07. Okay, so the probability of getting our data, or something more extreme, which means getting a difference of 1.3 or more, or positive 1.3 or more, or negative 1.3 or more, is 0.07. Okay, so I want you guys to try to think of, like, so this was just one example for like a t-test, but it's a good idea to kind of go through and say, like, what does it mean to get a p-value of this for, I don't know, one-way Anova, or for this other type of test. Okay, so think about what exactly a p-value means here. And I think this is something maybe some of you guys could work on, because as I was reading through your lab 4s regarding that research article, some of your answers for what the p-value was not quite right. Okay, so and then other things, the p-value is not a probability about the null hypothesis. Okay, the p-value is not the probability that the null hypothesis is true, or that the alternative is true, or anything like that. The p-value is also not about your sample. It's always about the the p-value is always about the probability of observing your sample. If the null hypothesis were true. So the p-value is the probability of getting your sample if the null hypothesis, and the null hypothesis is always about the population, a statement about the population is true. Okay, the hypotheses are never about the sample either. Okay. All right. What else is there to say? Okay, let's talk about type 1 and type 2 errors. Oh, I saw a funny comic on type 1 and type 2 error. Let me see if I could pull it up here. I shared it with my other class. So let me Oh. Is this gonna work? Maybe it's not that funny. Story of my life. Okay. Yes, here it is. Okay, so this is type 1 error. Can you guys see this? So the one thing that this thing is missing would be the null hypothesis in this case would be, what? What would the null hypothesis here be? If this is the type 1 error and this is the type 2 error.
I thought a type 1
Not necessarily. Why? And I don't know which one's worse.
What was the original question?
So if this is this is the joke, right? What is the null hypothesis in this in these pictures here? If the type 1 error is telling a man that you're pregnant, and type 2 error is telling a pregnant woman that she's not pregnant, what is the null and alternative hypothesis? Null hypothesis would be patient is or is not pregnant.
Is not.
Yeah, the patient is not pregnant. This is the kind of the null assumption, and then the alternative would be patient is pregnant. Okay, so if these are the null and alternative hypotheses, then type 1 error indeed is telling a non-pregnant patient you're pregnant, and telling a pregnant patient you're not pregnant would be a type 2 error. Okay, so anyway, be able to identify type 1 and type 2 errors. What else can I say about type 1 and type 2 errors? Okay. Know the relationship. And what is the relationship between type 1, type 2, alpha, beta, power, and type 1 and type 2? Did we not talk about power? Oh, okay. Then, really? I didn't talk about it? Okay. All right. I better double.
I asked about it a while back, and then you talked about it, but you said you weren't going to cover it.
I wasn't going to cover power calculations. No? Okay. Well.
Then you asked about beta.
All right.
Yeah, and then you mentioned power.
So alpha is the probability of what? Type 1 error. So there's probability of doing what? Falsely rejecting the null. Beta is the probability of type 2 error. Okay. So then let me I'll say power is equal to 1 minus beta. So whenever you do 1 minus something, and it's a probability, you get the probability of what? No. So if we say if beta is the probability of a type 2 error, 1 minus that would be the probability of
the alpha.
No.
The opposite.
Yeah, it's the probability of not a type 2 error. Okay, so 1 minus beta would be probability of not a type 1 error. So what is it? I'm sorry, not a type 2 error. I apologize. So what is not a type 2 error? No. Okay. All right. Maybe this is good that we're covering this. Okay. So let's fill this in. Okay. So our decision is to reject the null. Our decision is do not reject the null. Okay. And then this is given the null hypothesis is true, or given the null hypothesis is false. Okay. Rejecting the null, given the null hypothesis is true, this is a type 1 error. Rejecting the null given the null hypothesis is false, this is and this is the correct decision. Okay? If the null hypothesis is false and we reject it, that's a good thing. Okay? Given the null hypothesis is true and we do not reject the null, what is this?
Correct.
This is correct. And given that the null hypothesis is false and we do not reject it, this is a type 2 error. Okay. Okay, so a type 2 error can be thought of as do not reject given null is false. Okay, so a not type 2 error, so not committing a type 2 error would be what? So I'm just going to get rid of this not, and this will be do reject the null, given that the null is false. Okay? So, and this would be, basically the probability of this would be the power. Okay? So that's this box right here. This box, the probability of this box, this is the power. This is the power is the probability of correctly rejecting the null given that the null is false. Okay, so that's a good thing. We want tests that are powerful. I didn't talk about this when we talked about Wilcoxon Mann-Whitney tests and how Wilcoxon Mann-Whitney tests were less powerful than their non-parametric tests were less powerful than their parametric counterparts. I did say that, but I didn't talk about the definition of power. Okay. All right. All right. Well, this is what it means to have a powerful test. Okay. So a powerful test is going to correctly tell you when to reject the null more often than a less powerful test. Okay, so you can think of it as kind of like cranking up the sensitivity of a test. Okay, so I don't know. So maybe you have like you can install like a motion detector or something that will turn the lights on when something walks by. Okay, you can crank up the sensitivity so that you're essentially increasing your alpha. Okay, but by cranking up the sensitivity, you're increasing your alpha, but you're also increasing the power, meaning it's going to correctly identify when somebody walks past. Okay, but it might get so sensitive that it's triggered when cats walk past the motion sensor or something like that. So, so that's what we have. Yes.
The power test will tell you not to reject the null more often, or to
So the power is related to the probability of rejecting the null when the null is false. Okay, so in our decision tree, okay, rejecting the null is related to alpha. Okay, So if we increase alpha, both type 1 error goes up and the power goes up, because increasing alpha causes this decision to reject the null. That's going to just go up in general. Okay? So increasing alpha is going to cause type 1 error to go up, but it's also going to increase the power of your test. Okay? So if we increase alpha, we're going to be rejecting the null more often, right? Leads to rejecting the null more often, and that could go both ways. Okay, this would increase type 1 error if the null is true, but it also increases power. Okay, so rejecting the null more often has the effect of increasing your power, but also increasing type 1 error. So you just kind of have to say, well, what's a good alpha? If you want to increase your power without increasing alpha, you have to gather more data.
So in the example you were using about a street light,
Okay.
or a motion detector,
Sure.
The null hypothesis would be that nothing is there.
Yeah, the null hypothesis would be its default state, which would assume nothing is there.
Okay.
Okay? And then it would turn on when there's data that suggests something is there. Okay? And so when it turns on, that's essentially rejecting the null. If it turns on when a person walks by, that's a good thing. If it turns on because a squirrel ran by, maybe we don't want that. Or maybe we want that. I don't know. Okay?
Power is always 1 minus beta.
Yes, power is equal to 1 minus beta.
1 minus alpha.
1 minus alpha is the specificity of a test. Okay? So power can also be known as the sensitivity of a test and the specificity of a test. These are more medical terms, talking about like biopsies and stuff. So when you get like cancer screenings and stuff, they want tests that are powerful, but they also don't want people to undergo cancer treatment if they don't actually have cancer or something like that. So your initial screening will generally be very sensitive, and then follow-up screenings will be more specific. Okay. That's what we aim for, right? We want to minimize type 1 and type 2 error if possible, but can't. Okay, when do we want big alpha and when do we want small alpha? Big alpha desired when?
When you're trying to cast a wide.
Okay,
Less
so we don't want to make type 1 errors, but we have to choose. Like, we have to decide, is type 1 error worse or type 2 error worse? Okay, so big alpha desired when type 2 is worse. Okay, so big alpha is desired when type 2 is worse, and small alpha desired when what? Type 1 is worse. This is okay. Okay. Remember, how does directionality work? Directionality in the alternative, what do we do when we do directionality?
Greater or less than.
Okay, so that means, alternative has greater or less than, but what do we do differently versus a non-directional?
We either, sometimes you divide the p-value with that.
Okay, so you if you have like the chi-squared table, you would take your tail area and divide by 2. If you have the t-table, when it's directional, you leave it, but when it's non-directional, you multiply by 2. But we're missing an important thing. Regarding directionality.
It says that
We should always do a directionality check. Okay, so we should always check directionality. And what does it mean to check directionality?
to see if the data fits.
Yeah, to see if the data could even be used to support the alternative. Data fits what the alternative says. Okay, so if the alternative says mu1 is greater than mu2, but the data says y bar 1 is less than y bar 2, what's going to happen? Well, you're doing a hypothesis test, so what does this mean about what does this say about your p-value and your conclusion? So what does it say about our p-value? Essentially, when this happens, your p-value is going to be over 50%. Okay. Whatever it is, it's going to be more than 50%. It's technically going to be 1 minus the p-value if the directionality were correct. Okay. So if the directionality were correct, you'd probably get a p-value of like between 5 and 10% or something like that. And then in that case, if the directionality doesn't line up, it's technically 1 minus that 5 to 10%. So your p-value ends up being between 90 and 95%. Okay, but also you can just say, well, my p-value is going to be over 50%. Okay, and the conclusion will then be you're going to have no evidence to support the alternative. No evidence to support the alternative, which means no evidence to reject the null. Okay? There may or may not be a few questions on the test where you should do a directionality check somewhere in there before just taking your p-value and multiplying or dividing by 2 or something like that, okay? Because sometimes we just jump straight to what we think we're supposed to do. But we should always just kind of step back and say, hey, does this even make sense, all right? All right.
Can you write down what for each test you have to divide it and multiply it?
Oh, okay. Well, that's all written on your reference tables, but yeah, we can talk all about that. Let me just make sure I'm covering all of the conceptual topics I want to cover. Okay. So we'll crank it way back. Big pictures of statistics. Anyone want to tell us what statistics, what we're doing? Numbers. Hypothesis test. Yeah.
Variation. Variance.
Thank you. Yeah. Okay. I'm gonna note to self: don't ask these questions. Okay.
Data.
All right. So we are trying to make conclusions about the population based on samples of data. All right. So we're trying to, essentially, we want to make conclusions about the population based on a sample of data. Okay, so here's our picture, here's the population. What is why can't we study the population?
It's too big.
It's too big. Too big to be observed directly, right? Too big to study directly. So what do? Yeah, so we take a little piece out of the population. We sample it, okay? Now, what has to be true about our sample in order for our statistical inference to even make sense? It has to be representative, okay? So the sample must be representative of our population if we want our conclusions to be valid. Okay. Now, one thing that should give representative samples but does not guarantee representative samples is simple random sampling. Okay, so that's an important thing. So simple random sampling should give representative samples, but is not guaranteed to do so. Because it's random, right? There's a funny, again, maybe not exactly funny, but there's a comic. Let me see if I can find it. I'm in the mood for finding these dumb comics here. All right, Dilbert Cat Random Numbers. Is this it? Here, okay. So this is, can you see this? I hate these ads. Okay, all right, so it says, over here we have our random number generator, 99999. Okay, and he says, are you sure that's random? And he says, that's the problem with randomness, you can never be sure. So that was the joke. Okay. I thought it was funny. It should give us representative samples, but it's not guaranteed to do so. Okay. So our sample must be representative of the population if we want our conclusions to be valid. And then basically, what we observe in our sample, based on what we observe in our sample, we try to make conclusions about the population. Now, how do we obtain random samples and how do we get our data? Or I should say, how do we get our data? We can get them through experiments and observational studies, right? So as far as well, I would, what do you think is the key difference between an observational study and experiment? Okay.
Experiment, you prescribe treatment.
Okay, so in experiments, treatments are assigned. Treatments are assigned. Okay, we try to control factors of variation. Okay, observational studies, we just observe, right? And then, so what is this, what is the main effect that this has in terms of our ability to make conclusions?
For observational studies, you can only make conclusions about, there's like a problem like this in the homework.
Okay, yeah, so
You can only make conclusions based on what you observe.
okay.
Association.
Yeah, so observational studies, you can only make statements about association. You can only say these two things are associated. With experiments, you can make, what would the flip side be?
Observations of causation.
Yeah, causal conclusions. So with an experiment, you might be able to say, assuming the data supports this conclusion, you might be able to say this is caused by this. With observational studies, all you can say is there is an association between these two things, okay? So the conclusion is association. Okay, and the conclusion over here causation, okay? Assuming the data supports these conclusions. Okay, we make conclusions about the population, and our conclusions about the population are based on whether the data we have could have been a result of random chance or is an indication that something other than random chance is occurring. Okay.
In causation, right?
Huh?
With causation.
So either with association or causation, in terms of rejecting or not rejecting the null, it's, does our data have a high probability of happening just from random chance? Or is our data very unlikely to occur from random chance alone? That's essentially how we're making our conclusions. Okay, so shall we just blitz through all of our inference methods that we've covered? All right, let's do it then. Okay, so we'll start off with the t-test for independence. Or, I'm sorry, not independence, independent groups. Independent groups. They're making a second Independence Day movie, which... It's like,
Will Smith?
huh?
Will Smith?
No, not Will Smith. There's
Jeff Goldblum.
Jeff Goldblum's in it, and then it appears. Well, I have no idea. There is one of the main characters is black, and it seems it could be a story about the son in Independence Day. It could be like him grown up now. I have no idea. This is all speculation on the internet about the plot of the movie, so.
Oh yeah, it is.
Oh, it is?
Well, he's good. Yeah, his name was Dylan. I remember.
Okay. Well, then it is. All right, t-test for independent groups. Okay, so our hypotheses here is mu1 equal to mu2 or mu1 minus mu2 equal to 0. The alternative, mu1 not equal to mu2 or, you know, greater than or less than or whatever, right? And then the question is the observed difference which is y bar 1 minus y bar 2, is this observed difference, quote, significant? Okay, and the way we answer that is with our test statistic. We take the size of our observed difference and we divide that by our standard error. We compare the observed difference that we have to our standard error. Our standard error is given by this formula. And we look this up in the t-table with n1 plus n2 minus 2 degrees of freedom. Okay? So if, double the tail area, and if the alternative has a greater than or less than, check directionality first, and then assuming, and if the directionality is met, then your p-value is equal to the tail area. Got all this? Not yet. All right, let's talk about the t-test for paired data. So here, your null hypothesis is that the mean difference is 0, and the alternative will be that the mean difference is not 0 or greater than or less than. And then the question is, is our observed difference, which is d bar, significant, right? So here your test statistic is going to be d bar divided by the standard error. The standard error is the standard deviation of our difference column divided by the square root of n. Yes?
Sorry, really quick, for the greater than and less than sign, it's 0. So
Yeah,
it has to be
greater than 0 or less than 0, yeah.
And then for the one before that, is it just, it's greater or less than each other?
mu1 greater than mu2 or mu1 less than mu2. Or, if you write it this way, it would be mu1 minus mu2 not equal to 0, greater than 0, or less than 0, if you're going to write mu1 minus mu2. Okay. All right, and then,
Sorry.
what's that? Yeah. Okay, and then here you just look up in t-table with n minus 1 degrees of freedom. Okay, n is equal to the number of values in the difference column. Okay, and then we have the Wilcoxon Mann-Whitney test. Okay, we use this as an alternative to the t-test for independent groups. Okay, used when you have small samples and outliers exist in the sample. Okay, so this suggests that central limit theorem conditions are not met. Okay, and so the way this works, your null hypothesis, there's no symbols here, is just that population 1 and population 2 produce values from, that follow the same distribution. And then the alternative would be one population tends to produce larger values than the other population. Okay, this would be the non-directional. Okay, and then if you want to make it directional, just name this and just say population 1 tends to produce larger values than population 2, or population 2 produces larger values than population 1. Okay. And then, you do that process of count how many values, right? So your U statistic is equal to, the sum of the counts of the number of values in the other column that are smaller, right? Sum of the counts of smaller values in the other column. I don't feel like writing out the entire procedure here, but I'm hoping you guys remember that. Okay, and then you just look this up in the Wilcoxon Mann-Whitney table. We have a special table for this, okay, with n and n prime, okay. The larger n is the larger n. The larger of n1 and n2 is n, and the smaller is n prime, okay? Wilcoxon Mann-Whitney table assumes non-directionality, assumes a non-directional test if it's directional and directionality is met, you would take your table headings and divide by 2. So if directional and directionality is met, divide headings by 2. My hand gets tired too. All right. So that was that. What else? We have the. Okay, so we'll keep going. All right, let's do a one-way ANOVA. Okay. The null hypothesis will be what? mu1 equal to mu2 equal to mu3 equal to the grand mean, or the null hypothesis could also be written tau1 equal to tau2 equal to tau3 equal to 0. Okay, so mu would be group means. Mu sub I is group mean, or mean of group I should say. Or mean of population I. And over here, tau sub I is equal to the effect of group I. Okay, so it could be expressed either way here. And then, okay, and then the alternative is at least one mean different. One mean is different, and over here the alternative is at least one group effect not 0. Okay, so anything with more than 2 groups is going to be non-directional, okay? And then you, to do this, you build up your Anova table with source is between groups, and then within or residual. And you've got your degrees of freedom, which is number of groups minus 1. And this is the total would be number of basically your n minus 1, and so this is number n minus number of groups. And then you have your sum of squares, which is y bar minus y double bar quantity squared times n added up. And over here, you have y minus y bar squared added up across all groups, which is equal to n minus 1 times s squared added up across all groups. Your mean squares is always sum of squares divided by degrees of freedom. And your f is mean squares between divided by mean squares residuals, also known as mean squares error. Look up in t-table. With numerator df and denominator df. Okay. I'm sorry, not t-table, f-table, f-table. One-way Anova. All right, we have correlation and linear regression. Okay, we have correlation R is equal to 1 over n minus 1 times z sub x times z sub y. So we're taking our z-scores of x and y, multiplying them and adding them up. This essentially becomes n minus 1 times 1 over s sub x times 1 over s sub y times the sum product of this the linear least squares line minimizes the sum of squares residuals it is given by y hat equal to b0 plus b1x. b1 is equal to r times the standard deviation of y divided by the standard deviation of x. b0 is given by y bar minus b1 x bar. A residual E is the difference between the actual value y and our prediction y hat. Okay. Test for significant correlation. Null hypothesis, rho equals 0 versus the alternative that rho doesn't equal 0, or rho is greater than 0, or rho is less than 0. This takes a test statistic of r times the square root n minus 2 over 1 minus r squared. Look up in t-table with n minus 2 degrees of freedom. Alright, so what do we have left? Chi-square tests? I think that's it.
Is that the one with the p hat?
P hat, we have P tilde.
P tilde.
Yeah,
I
that's
thought we also had p hat. That's p count. That's p count, right? Or like.
P hat is our sample proportion.
Okay.
Yeah. Yeah, so we have the confidence interval. Okay, so I'll do that. Confidence interval for P. Okay, so we have P tilde. This is our Wilson adjusted proportion. This is y plus 2 over n plus 4. And then your confidence interval for p will be p tilde plus or minus 1.96 times the standard error. The standard error is equal to the square root of p tilde 1 minus p tilde over n plus 4. Okay, and then you'd say I am 95% confident that the proportion of blank in the population is between blank and blank. Okay, and then related to this would be the chi-squared goodness of fit test, where basically your null hypothesis states that probability of category 1 is equal to, P1. Probability of category 2 is equal to P2, etc., etc., etc. The alternative is at least one of these proportions is wrong. You have to create you have your observed values, and they're all counts. And then the expected values, which is going to be basically your n times, P1, n times P2, etc., etc., etc. And then your chi-squared statistic is observed minus expected squared over expected, summed up. And then you look up in chi-squared table with number of categories minus 1 degrees of freedom. Okay. You can have a directional test if there's only 2 categories. Okay, directional test is possible when there is only 2 categories. Okay, and when you have only 2 categories and you have a directional test, then you check your directionality, and if directionality is met, then you can divide your column headings by 2. Yes?
So are we not going to have, binomial distribution?
Yeah, we didn't learn any binomial distribution related tests.
So don't really concentrate too much on midterm 1
Yeah.
stuff. So it's after midterm 1. Okay. And that starts with chapter 7, right?
Yeah. Second chapter 7, maybe. Let me just check, make sure I'm not lying to you guys.
Oh, it starts in chapter 6.
Oh, the end of chapter 6, yeah. The end of chapter 6 with the confidence intervals, yeah. So, or chapter 6. Yeah. Okay. All right, and then lastly we have chi-squared test for independence. Your null hypothesis here would be what? That they're independent, okay? Variable 1 and variable 2 are independent. How do we express that symbolically? we would write something like probability of A given B is equal to the probability of no, A given not B. Okay? Or possibly also equal just to probability of A. So if they're independent, then these would hold true. A given B is equal to A given not B. Okay? We wouldn't, so, you know, not true statements would be probability of A given B is equal to probability of B given A. This is not going to be true. Or probability of A given B is equal to probability of not A given B. Okay? These will not be true. Okay, and then the alternative will be something like probability of A given B is greater than probability of A given not B, or, you know, or not equal to or less than, okay? Basically saying that, you know, if B has happened, then the probability of A either increases or decreases or something like that, saying these two categorical variables are related, right? Like the probability that someone voted for Bush is higher if that person was Republican, okay? Or something like that. So that would be the null and the alternative. Okay, and then, you know, you have your observed table. And then you create your expected counts if the null hypothesis were true. Okay, and then so that basically the cells are row total times column total divided by grand total. The expected cell count is that. Your chi-squared statistic, observed minus expected, quantity squared over expected, summed up. Degrees of freedom, number of columns minus 1 times number of rows minus 1. Whew. All right. I think that's everything. Yeah. All right, so, you know, just be comfortable doing all of this stuff. You guys have been, like, knocking it out of the park every quiz and stuff, so I'm sure you guys will be fine on the final exam, all right? I mean, of course, study, please. But you guys have been doing great. All right, have a great week, and good luck.